Okay, now they've allowed me to come in the room to at least film a lab, and so we're going to do a lab on springs right here. So what we're going to do is we're going to hang a spring right here and call this point right here is the unstretched position of the spring. That's where S equals 0 right there. Then what we're going to do is we're going to put selected weights onto the spring right here. And we're going to measure how much it stretches down right here. And what we want to do is we're actually, if you come over to here, we're going to have put 0.1 kilograms, see how much it stretches, 0.2, 0.3, 0.4, 0.5, all the way down to 1. And this will tell me how much it stretches right here from the equilibrium. We want that in meters right there. Okay, so we're going to get that S right there. And well, you'll notice when this thing is just sitting there, these two are in equilibrium right here. mg and ks are the same. And so if we were to take the data for putting it here, putting this point here, for S, this is S right here, versus mg, what we're going to get is we're going to get a straight line right here. Why? Because if you set these two equal right here, you get ks equals mg, or k is, mg is my y, I'm going to just write it like that, mg up here is my y-axis, and s is my x-axis, so this is like a y equal ks curve. Well, that's just a straight line that goes through the origin. Y equals mx plus b. S is like my x right here. So this is just going to give me a straight line like this, and the slope is what's in front of here. It's my k. So what we'd like to do is we'd like to get the value of k right here, which is the value of the slope. The slope here, slope equals k. Now we could just draw a line through it and try to eyeball it, but I think a better way of doing it is if you go onto the web and you look up linear regression calculator, and what that'll allow you to do is put in a bunch of xy points, x1, y1, x2, y2. You're just putting in all these points right here, and then say calculate, and what this will give you is it'll give you the best equation of that line. It'll give you the best slope, and it'll give you the best y-intercept. We're not using the y-intercept here, but it'll also give you the best y-intercept just from a bunch of xy points. So look this thing up. There's a whole bunch of them on the web. Just pick one of them and it'll give you a little table. You put in the xy values, hit the button, and it'll give you the best slope, and some of them will even plot it out for you right here. But and then if he plots it out, then you can even take a snapshot of it, because that's what you're going to send to me right there. So I need the value of k, which is the best slope right here. So the best slope will equal the value of k. So now we've got the k one way right here, just from making this plot right here. We'll take the data in a minute right here. Now, there is another way we can find k. I'd like to find it a different way right here. And that is, if you were to give this, pull it down a little bit further and let it go, it's going to oscillate right here. And later on, not for a little while, we'll calculate the time it takes to go back and forth. I'm just going to give it to you right now. But for a massless spring right here, for an ideal spring, it's given by this. It's given by 2 pi times the mass of the object over k right here. And so hopefully if we can measure the time and measure the mass of the object, we can get k this way right here. But this is for an ideal spring. We have springs that have mass right here. And so that means how do we handle when the spring does have mass? Well, you can't just add the mass of the spring in there because not all the spring goes up and down. Only, this top ring hardly moves at all. This bottom ring is moving quite a bit, so only a part of the spring is going up and down. So here I said, well, instead of using all the spring, why don't we say it's some fraction of the spring? Where that right there is some fraction. It's got to be between 0 and 1. 0 and 1. If it was 0, it'd be a massless spring. None of it would be going up and down. If it was 1, then all the spring would be going up and down. So you're going to get some number between 0 and 1 for that. We'll calculate that right there. So what we want to get is we want to get the value of k, and we want to get that epsilon right here. Well, suppose we came along here and we plotted out the mass versus the time it takes to go up and down, the period right here. Well, if that's my y and that's my x, that's in the square root, and you get something that looks like a square root function. I don't want any square roots in there because it's hard for me to fit square roots. It's easier for me to fit straight lines. So what we'll do is we'll square this. If we square both sides, then what do we got? We got t squared equals 4 pi squared m over k plus 4 pi squared epsilon ms over k. Epsilon ms over k. Well, so now, instead of plotting out t, we're going to plot out t squared. So now, this is my y-axis. M is my x-axis. This is all a constant right here. We could call it C1. And this is all a constant because that's the mass of the spring. That's not changing. C2. And you notice isn't that the C1 right here would be the best slope, and that would be the y-intercept. So what we'll do is we'll run this linear regression calculator, but for our x, we'll use m. For our y, we'll use t squared right here. And if we plot out this versus that, we should get a curve. We should get a line that goes like this. It has a y-intercept and a slope right here. And now, when we go to linear regression calculator, it will give me the best slope right here. The slope here of this one, the best slope, is equal to everything here. It's equal to 4 pi squared over k. So that's equal to 4 pi squared all over k. So we can then find the spring constant by moving the k over here and putting the slope down below right there. So k is just 4 pi squared over the slope of the line right there. Okay, so now we can compare these two values of k. You can get a percent error right there between these two values of k. So now we've got two ways of getting the k. Then, when we use that linear regression calculator, it also gives me the best y-intercept. Well, the best y-intercept is right there. So take the value you got from the best y-intercept with this data and set it equal to this value. So the best y-intercept is equal to 4 pi squared epsilon ms over k. 4 pi squared m sub s over k, epsilon. Well, we know what the best y-intercept is. We know what the k, we'll use the k from right here. We'll measure the mass of the spring in just a minute, and we know 4 pi, so we can calculate that epsilon, and that's what we want. So now we'll go and we'll do the experiment right here. We'll measure it all, and then you can go ahead and put this data in. But you're going to have to, when we measure the time, you're going to have to do it with your own phone, because I'm not going to measure the time. You can do it in real time right here. And so what we're going to have is, here I have this table right here. We're going to have different masses from point 1, point 2, all the way up to 1. We'll make a column of all of our S's right here. We'll make a column of all of our times right here. We'll then multiply this one by G to get our column of weights. And then we'll take this column and we'll square it to give me this one over here. And so then what are we going to do? Our two plots are mg versus s. That's our one plot. And our second plot was t squared versus the mass right there. And so for that next one, that's what we'll calculate. We'll just do that in the next in the next video right there. Okay, so now we want to take the data on this. The first thing I'd like to do is get the mass of the spring. So we'll just take and put the spring on here, and the mass of the spring is 164.9 kilograms, or 0.1649 kilograms. So the mass of the spring is 0.1649 kilograms. Okay, remember that. You're going to need that number. Okay, so now we can put the spring up here. It doesn't matter too much which way we put it, as long as we're consistent. We'll keep it right here. Okay, so from right here, if I look at the height right there, this height, it depends on where we measure it from, but what I get is I'm going to adjust the height here so that it's at a nice value, and right there, that little dip is right at 170 centimeters from the floor. So we're starting from the floor, where all of our distance are going to have to be measured from the floor up. It's at 1.7 meters right there. That's my initial spot right here. That's going to be my S sub naught right there. So all of our distances are always going to be measured relative to that 107 or 1.7 meters. Okay. So the first thing we want to do is put in 100 gram weight right there, the 0.1 kilogram, and see how much it goes down right here. Okay, so right there, I get 101.6 meters. So that must mean that the first distance, if it went from 1.7 to 1.6, our first distance is 0.1 meters right here. So you're always going to take this minus the height of the next one right here. Okay, so now we've got the first S1. Now we want to move this up and down right here, and now we want to measure the period of oscillation. Now you could just say start, stop, and get the period, but that's not a very good way. We would be much better measuring the period for 10 oscillations and divide it by 10. So get out your phone and put it on the stopwatch, and you're just going to measure 10 oscillations. So you're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, stop right there. And so now you take that time and divide it by 10, and that would give you the time for this one right here. You might even do it a few times just to make sure that you get the correct time. Just make sure when you're measuring you go 0, 1, 2, and then stop at 10 right here. Okay, we put the next mass on, 0.2. 0.2. Well, that distance is 1.5 meters. 1.5 meters. So my S2 would be from here to here. That's my S2 right there. Then we want to measure the period of oscillation. So again, we'll let this thing go many times. Go ahead and measure the period for 10 oscillations. Just make sure when you start you go 0, 1, and then 10 right here. So I'm just going to let that go for a minute right there. Measure the period for 10 oscillations and divide it by 10 right there. Okay, now we'll put on 0.3, so we can just sum these two together right there. So now we're at 0.3 right there. Now our distance is at 139. 1.39. So our next S is be this minus that right here. It's how much you've stretched right there. Now we can go ahead and we can measure the period of oscillation here. So again, measure the period of 10 oscillations. I'll let that go for a little bit. We'll measure the period for 10 oscillations. Okay, that's probably enough right there. Okay, now we'll put on 0.4. 0.4 kilograms right here. Okay, so now the reading is at 129. 1.29. So your next S is from here minus that. Right here. That's the next S distance right here. Now we can go ahead and we can measure the period of this one right here. Again, for 10 oscillations. You can even do it a few times just to make sure you got it down, and then divide it by 10 right there. Okay, that's probably good. Now we'll go up to 0.5, which is right here. We're going up in 100-gram increments, so there's 0.5 right there. 0.5, that's a little tricky to read, but that is, looking at it sideways, I have to pull it out a little bit right there. It's 119. 119, 1.19. Okay, now we want to get the period of oscillation of this one right here. You notice the period is getting slower. Okay, so now we have, there's 0.5 right here. Next, we'll put on 0.6 right there. So that takes me down to about 108. 1.08. Again, S is this minus this. Now we can measure the period of oscillation for that one. Right there. Okay, remember on the video you can back up and look at it again and again, measure it often again. So then we'll go up to 0.7. 0.7, which would be right here. Now we're down to about 98.98. Now we can get the period for that one. Okay, now we can go down to 0.8 right here. Now the distance is at 88. 0.88. 0.88. Now we can get the period. Okay, now we can go down to 0.9. And that is around 77.77. 0.77. Okay, now we can get the period of that one. Okay, and then one more right here. We're going to have point to 1 kilogram. 1 kilogram. Now we're down to about 0.67. 0.67. 0.67. Then we can measure the period of that one. Okay, so now you have all the distances. Remember, it's always this minus this minus this, and so on. So if we turn this around, we know what all the masses were. We just calculated the S's. You measured the time for 10 oscillations divided by 10. You take this column, multiply it by G to give you this column. You take this column and square it to make that column right here. And then you're going to come over to here and you're going to plot out S along the X direction, MG along the Y axis. You're going to use those points right there, these points, plug it into linear regression calculator, and it'll give you the best slope and the best y-intercept. All I care about is the best slope. The best slope will give me the K value. Then we're going to plot out t squared. You have a column of t squared versus m, and take all those numbers and plot it out and put it into linear regression calculator and have it give you the best slope and the best y-intercept. The best slope will be 4 pi squared over k. Since you know what the best slope is and you know what 4 pi squared is, you can get k. K is 4 pi squared over the best slope. We can compare the two values of k, give me a percent error. Also over here, this is the best y-intercept. Remember, the linear regression will give me the best y-intercept, and that equals this, and we know what the 4 and the pi and the mass of the spring is. We know the k because we're going to get it from this guy up here. And so we know everything here. We can solve for epsilon right here. And hopefully epsilon is a number somewhere maybe to 1/3 to 2/3 or somewhere in that range right there, because that tells me how much of the spring is actually going up and down. So that's what we want. Once you get these plots right here, and all this information, again, send it to lab dump 2, I think, or it might be 2 or 4. It's the last one. Okay, then that should do it for that lab.